A warm welcome to everyone who just joined to our Support Vectors weekly paper reading. Those of you who are here for the first time, a really warm welcome to you. I invite you to join our Discord channel too, so that you could interact with people after the meeting and propose new papers to read in the coming weeks. I would now like to introduce Adarsh. Adarsh is doing his internship here at SupportVectors. As you know, SupportVectors is a research and training place where people not only do research projects, but they also get trained in here. We offer lots of workshops and so forth. And he's a first-year student at University of Illinois at Urbana-Champaign, and quite a bright student. In a very short time, he has picked up the topic that he's doing his internship on, namely graph neural networks. So with those words, I will yield now to Adarsh. You will be there. Your life. Just start speaking.
All right. Hello, everyone. I'm Adarsh, and tonight I'll be presenting on graph representation learning. So, what is graph representation? Okay, so for tonight, we're going to talk about what is graph representation learning, and we're going to focus on node embedding techniques that are using random walks, as well as graph level embeddings. So first, to discuss graph representation learning, we need to discuss what graphs are. So a graph is a mathematical structure that is able to represent the relationship between nodes and edges. So here we have this like mathematical equation where we say G equals VE, and V is the set of vertices or nodes, and E is the set of unordered pairs or edges. So we can see here we have the set of vertices and the set of edges, and that gives us this graph that we see here. So this is a nice picture, but what is it used for? Well, graphs are useful because they can represent anything. Nodes can be the people watching this presentation right now, and the edges can be the relationships between everyone, and that would make the graph a social network. Or alternatively, the nodes can be power stations, and the edges can be transmission lines, allowing the graph to represent an electricity grid. So as long as we have an idea of what we want the nodes and edges to be, we can pretty much represent anything through a graph. And there are also different types of graphs. So when the edges represent like a mutual connection, like a handshake or a friendship, we call that undirected graphs. And you can see that the edges are just straight lines. But for a directed graph where the edges are not necessarily mutual, like say if you're following someone on social media, that's not necessarily a mutual connection. So in that case, the edges become a set of ordered pairs, and then directionality matters. You can see we have the arrows that identify how the connection flows. We also have a special type of edges called a self-loop, where a node can have an edge pointing to itself, like we see on node C. But this isn't restricted to directed graphs. It's just that you might see that kind of self-loop on like a state diagram where you want to repeat a state. So if we want to apply machine learning techniques to graphs, traditionally what we do is like given an input graph, we would extract the node features from the graph and learn a model that maps the node features to labels. And labels are just will depend on the target space. If we're talking about a social network, the labels are going to represent people, for example. If we're talking about the electricity grid, the labels could be about power stations. So traditionally, the feature extraction of node features is accomplished through feature engineering, which is this manually working with the graph to pull out the node features, edge features, graph level features, and so on. But the big problem with feature engineering is that it's really inefficient, and it's also only really tailored for a single type of graph. If I was to make a graph of this everyone watching this presentation right now, and work with that like graph, like do feature engineering in order to get everybody's like relationship information, personal information, and so on. And I could create a model that works for this graph. But if I want to translate my findings to a new graph, that's not possible. If the new graph is about electricity grid or even just a different social network, that information is not applicable. So what we want to do is we want to automate feature learning. And that's all graph representation learning is. It's simply efficient feature learning for graphs using machine learning techniques. And one such technique is called node embeddings. So the goal of node embeddings is to encode network information through nodes. So we're converting each node to a unique vector embedding that holds information about each node, such as edges or neighbors. So you can see that we're taking this graph and we're moving it to the embedding space. And each node, so you no longer have to worry about edge connections. Each vector is going to have that kind of information just stored in itself. What we also want is that the embedding similarity should reflect the node similarity. You can see here that nodes U and B are connected by an edge. So ideally in the embedding space, the vector embeddings for U and B should also have some similarity. In addition, we obviously want to use node embeddings for prediction tasks. For example, for node classification, the picture here is of a program called NetProbe, which crawls through online auction sites and represents sellers as nodes and the transactions between them as edges. And it's able to identify benign or fraudulent sellers based on those transactions. We can also use node embeddings in link prediction, which is like predicting future edges between nodes. So here we have an example of a social media network where users are nodes and message channels are edges. And so we're trying to predict future message channels based on existing relationships. So we can see here that Adam and David are likely to talk with Sophie in the future because they have Maya and Maria as mutual friends. You can also see link prediction in online recommendation systems where new content is recommended to users based on the content they've already consumed. We can also use node embeddings for clustering. Here we have a crime map in Ottawa where areas of high crime incidents are specifically identified. So whenever we wanted to identify communities or just significance groups within a graph, we can use clustering for that. And we can also use node embeddings for anomaly detection. So this picture is of root cause analysis in a YouTube service system. And it would be difficult for a human to identify where the problem is originating from, but through node embedding, we can identify the root cause of an issue by determining which node isn't behaving like others. So how do these embeddings represent similarity? You may be familiar with WordVec, where the cosine similarity of vectors represents semantic similarity. So here we have the famous king minus man plus woman equals queen example, where through vector addition and subtraction, we're able to move from the king vector to the queen vector. And so we can easily see that the similarity between vectors basically represents how similar in meaning these vectors are. But we don't have this same kind of notion of semantic similarity for nodes. The cosine similarity for node embeddings depends on the kind of encoding system we use. And there are two different kinds of similarity that we can represent for node embeddings. So we have homophily and structural equivalence. Homophily is the idea that similar people group together, like birds of a feather flock together. And so if we're focusing on homophily, nodes that are close together should be considered similar. So for example, everyone here is interested in learning about graph representation learning. So if we were to convert everyone to node embeddings, everyone's node should be appearing roughly similar. And this is useful for node classification or clustering when we want to focus on the shared characteristics of nodes. Using this image that we see here, if we take embeddings for the red nodes, then ideally they should appear close to the embeddings for the blue nodes, since they all share edges together and they're close together. Alternatively, we can focus on structural equivalence. So it's the idea that nodes that share the same structural role in the graph should be considered similar. So for example, imagine there's a professor in China presenting on some topic in theoretical physics to an audience that's also interested in theoretical physics. So even though I'm over here in California talking to you about graph representation learning, and this professor is in China presenting on theoretical physics, we both share some structural similarity despite our geographic differences. So it's basically the idea that the nodes that share the same structural role in the graph should be considered similar. This is useful for link prediction or anomaly detection when we want to focus on broader patterns in the graph, such as structures in drug molecules. If we go to this image here again, if we create embeddings for the red nodes and we want to focus on structural equivalence, then the embeddings for the orange nodes should appear close by, since even though they're on the opposite sides of the graph, they share the same structural role. The problem is we can't easily represent homophily and structural equivalence at the same time. So we have to prioritize one over the other. So that's one trade-off that we have to make. So how do we represent nodes as vector embeddings, and how do we understand the relationship between these embeddings? We use an encoder-decoder framework. So for our encoding, we'll use like a shallow encoding system, and we call it shallow because the existence of edges is the only basis for node similarity. All other information is ignored. There are deep encoding systems which considered edge or node features, but that's a precursor to graph convolutional networks, which is beyond the scope of tonight's presentation. You can imagine it as a sequel to tonight. But basically, for a shallow encoding system, we're just creating a unique vector embedding for each node, and we're storing that in an embedding matrix, where you can see here. Every column in the matrix represents a vector embedding, and the height of the matrix is the dimensionality of each vector. So for our decoder, what we want to do is that we want to take in two nodes and reconstruct the relationship between them. So the output of the decoder should reflect the node similarity. You can see this like sort of this equation here. SUV is like a hypothetical similarity function. So what we're trying to do is, given two nodes, U and V, we want to make sure that the vector embeddings reflect some similarity between the original two nodes. So one encoding system for similarity is called random walks. So some terminology, the vector ZU is going to be the embedding for node U. The probability of P of V given U is the predicted probability of visiting node V starting from node U. And the inner product of ZU and ZV is the probability that nodes U and V co-occur on a random walk. So the probability of P of V given U represents the node similarity, while the inner product of ZU and ZV represents the embedding similarity. So what does this mean? Okay, if we're taking a random walk is just a walk through the graph starting from node U, and at each step we randomly select the next node, and we store the walk in a multi-set so we can have repeats. You can see here that we're starting from node U, and then we're going to A, B, C, D, back to B, and then to F. And then we would store that in the multi-set. And so we would repeat these random walks in order to get an idea of the shape of the graph, so we use random walks because they're expressive. They capture the local and global structure of the graph. You can see that if we repeat the random walks a lot of times for a given node, it's going to cover those nodes that are close by, that are direct neighbors. But we're also going to get an idea of the larger structures that move beyond. You can imagine in your own life, you have those close friends or colleagues that you will always interact with, but you also talk to different people at your job, or maybe you have a favorite coffee place with people you talk to there. So this kind of random walk structure is able to represent both those like close friends as well as those like larger people you see. It's also efficient.
Hey Adarsh, what do the colors represent here of the edges?
Oh, the colors are just it's just like proximity. You can see like this. There's this node in the center. This node in the center. Yeah. It's just proximity from like the red nodes. The red edges are the ones that are closest, while the green ones are the ones that are furthest. Does that make sense? Yeah.
I see. Got it.
So random walks are efficient because we only need to consider the nodes that appear on the walks. Even though going back to the image, you can see that these two nodes, there is conceivably a path between them, but realistically, that's not going to be something that happens. So we're able to focus on the nodes that are most likely to occur, and we're able to discard the nodes that don't really have an effect on each other despite being connected. So for our encoding system, what we want to do is we want to estimate a P of V given U using some random walk strategy, and we want to optimize the embeddings to encode these random walk statistics. So to decode these encodings, we use the decoder function, which we define as the exponentiation of the inner product of ZU and ZV divided by the sum of every inner product for each node, which converts each vector to a probability measure. This looks complex, but it's basically just the reflection of the principle that the embedding similarity should reflect the node similarity. And the loss function for this decoder function is simply the negative log loss, which reflects our desire to maximize the correlation between the embedding and node similarity. One problem with naively computing the log function is that this leads to OV squared computation time and big O time. You can see that there's a V in the total sum, and as well as a V in the denominator of the decoder function. So we want to optimize this further. So the random walk.
Hey, Adarsh, this one question. So, is there a notion of number of steps encoded in the previous one? Like you could be 10 steps before you actually reach V in the random walk, or it could be the immediate one, but still the loss function seem to didn't account for that. Am I right?
Right. Yeah. So it's not directly in the loss function. This actually goes to the encoding step. Yeah, I'll go back to this slide. So when we say using some random walk strategy, that means we can describe like walk length or the number of walks that we're doing here, and then our loss function will work after that. So when we're talking about like number of steps, for example, that's part of the encoding. That's not part of the decoding step. If that makes sense.
I see. Okay, got it.
Yeah, so a basic random walk that I was talking about earlier is called deep walk. And so one optimization for it is called the hierarchical softmax, where we treat the nodes as leaves of a balanced binary tree to quickly evaluate the conditional probabilities. So here, they actually use hierarchical softmax in Word2Vec as well. So the principle is pretty much the same between them both. We represent the words or nodes as the leaves here. And if we want to determine the probability of, say, this node, we simply start from the root and then we just work our way down. And so this yields us the following parameterized log probability, which improves the computation time by reducing the V in the total sum to D, where D is a training set of random walks. And it's faster because it doesn't encompass all nodes in the graph. Another type of random walk is called Node2Vec, and it's a biased random walk that interpolates breadth first search and depth first search to create a neighborhood for node U. And a neighborhood is just those nodes are like direct neighbors, as well as like those are further away but like still part of that like community. So Node2Vec works by taking in two parameters: a return parameter P and an in-out parameter Q. So the parameter P is just a probability of returning to the previous node, while the parameter Q is the probability of exploring further in the graph. So here we have this this graph where where you start on node T, which is connected to V and Z, and then X and Y are further out. So when we move to node V as a result of the random walk, we can see that the probabilities of moving to a new node aren't equivalent. Going to X and Y, the probability of moving to X and Y, which are both new nodes, is dependent on Q. It's 1 over Q. While the probability of returning back to T is 1 over P. And we can see that the probability of going to node Z is 1. That's because node Z is a direct neighbor of node T, but we didn't directly go to it. Yeah. So one optimization for Node2Vec is called negative sampling, where we sample all the neighborhoods that we have, and we penalize those that are far from a given node U. So this gives us a normalized log probability, which is the negative log loss of the inner product, normalized by the logistic function minus the expected value of the noise distribution over V. Pretty complex, but let's break it down. We use the logistic function to map the inner product to a 0 to 1 range, which makes it easier to classify each input. And the negative log of this value once again reflects our desire to maximize the correlation between embedding and node similarity. And since we're doing negative sampling, we want to penalize the neighborhoods that are far from node U. That's why we subtract the expected value of the noise distribution. And to optimize this further, we can use stochastic gradient descent. So instead of evaluating gradients for all nodes in the graph, we only evaluate it for each training example. So this is a much noisier descent compared to typical gradient descent, since we're doing random sampling, which can lead to different different amounts of error, but it converges much more quickly. And so other types of random walks, the thing is that random walks are really modular per se, because you can easily modify them or extend them depending on the amount of walks or the walk length that you use. There are also just changes to the algorithm. For example, we have walklets, which successfully skip nodes and random walks. So you can see here that we have this graph that represents like successive layers of communities that we might be a part of. So what walklets does is that in order to represent each layer of these communities, it'll first do a basic random walk for those direct neighbors. And then once it's done that, in order to represent the next layer of the community, it's going to skip the nodes that's already considered. And so this allows it to bias towards homophily and just focusing on similarities between communities. Yeah. And we can there's also SupportVectors, which uses a biased random walk on a multi-layer graph to represent structural equivalence. So what SupportVectors does is that it creates a new graph on top of the existing graph that represents structural equivalence through proximity. So structurally similar nodes will share edges in this new graph, while structurally distinct nodes will not. And then it'll just do a biased random walk on the new graph. So yeah, you can see here that we have this we have this graph where like these red nodes, these red colored nodes share some structural similarity, as well as these yellow nodes and these orange nodes, even though they're physically apart in the graph. So which strategy is best? It depends on what you're trying to do. Generally, node-to-vec is better for node classification, while other random walk strategies are better for link prediction. Here we have just a graph that like colors the node embeddings based on what communities they're in. What we have here, an example of like link prediction using preference random walks, and preference random walks are just another type of biased random walk that take into consideration edge weight. So yeah, it just depends on what you're trying to do. Most of the homophily ones, most strategies tend to fall in the middle, unlike walklets or SupportVectors. So it really just depends. You might have to try out a couple of different libraries to get what you want. There are some limitations to the shallow encoding system, though. For one thing, it's computationally inefficient. The encoder is directly optimizing a unique vector for each node. So during the training process, we have to repeat calculations since every node has a unique embedding. And this could become infeasible for very large graphs, for example. In addition, shallow encoding fails to consider node features. Here we have a graph of like a dating site. You can see that some like the nodes aren't all the same, and the edges aren't all the same. We have user nodes, we have attribute nodes, we have like the city, state, country on this side, and we can see that the edges are also labeled in their own way. Like, yeah, this user likes this thing, and this user also likes this thing. They both hate another thing. So the problem is when we're doing a random walk, for example, all this information is going to be ignored. All the nodes are going to be treated the same. All the edges are going to be treated the same, which could lead to a loss of information during a learning process. In addition, shallow encoding is transductive, which means it can't be applied for inductive tasks. So what does this mean?
Hey, Adarsh, sorry, just one question. Can you not just like augment or concatenate these node embedding features with other features and then use your standard deep learning techniques to train them? Isn't that one way of incorporating these other features that you talk about, or am I missing something?
That's what you're talking about is more seen in deep encoding systems, which is more for graph convolutional networks. You're also kind of talking about like feature engineering for feature engineering that combines random walks, which is a strategy, but again, it's not replicable. You could do it for a given graph, but you would have to repeat that sort of extraction for every graph that you're working with.
I see. Okay. Yeah. Thank you.
So yeah, the shallow encoding system is also transductive. So say I'm adding a new node to this graph, and if I want to use the previous encodings that I had before. The thing is, the old encodings are no longer relevant to this new graph because these new nodes, this new node changes the relationship between the existing nodes. So this isn't very good for channel encoding isn't very good for node prediction, or it's not very good for learning. If I want to work with this new graph that has this new node, I have to go through the embedding process again. So say we want to look at the graph on a high level, not simply just the nodes. Well, we can use graph embeddings. So the goal of graph embeddings is to embed entire graphs or subgraphs as opposed to just nodes. So here I've like circled 2 subgraphs in the graph, and then we're converting them to two unique vectors in the embedding space. So we also want to be able to use graph embeddings in graph level prediction tasks. So we can use graph embeddings in graph classification, where if we're looking at molecule graphs, determining the toxicity of a molecule is going to depend on the structure of a molecule as a whole, rather than the constituent elements. We also want to identify anomalous subgraphs in a larger graph based on structural differences, such as identifying, like, say, a benzene ring and drug molecule. So there are several different graph embedding approaches. There's taking the sum or average of the node embeddings. There's the virtual node approach and the anonymous walk approach, which involves anonymous walk embeddings. So the sum or average of node embeddings is pretty simple. We just take node embeddings for each node in the graph, and then we just take the sum or average of the embeddings. And that gives us a graph embedding. And this is actually, despite sounding so simple, it's actually pretty successful. The one big issue with this is that you can't easily represent subgraphs. So one option for representing subgraphs is the virtual node approach. So virtual node, we take a graph or a subgraph, and then we create a virtual node that connects to every node in the graph or subgraph. So we can see for the graph, we can see here that we have this virtual node that shares edges with every node that we want to examine. And then we just take a node embedding of the virtual node, which is the graph embedding. The problem with this is still very successful, but the problem with this is that we're still looking at node embeddings. So if we want to look at the graph structure as a whole, what we can do is anonymous walks. So an anonymous walk is a random walk, but instead of the states corresponding to nodes, they correspond to the index of the first time we visited a node. So what does that mean? Here you can see that we have like a red and blue walk here, and they're covering basically almost entirely different nodes, but they still have the same anonymous walk because both of them start on So both of them start on one node, they move to a new node, they move to a third new node, go to a fourth, return to the third, and then end at the fifth. So we can use this we can use this to get an idea of the graph structure on a high level that isn't dependent on the node relationships. So as we increase the walk length, we're going to get a much exponentially larger number of possible walks. You can see that if we have like a length of 3, we only have 5, but 12 is going to have almost over 4 million. So for if we're using an anonymous walk to create a graph embedding, what we want to do is we want to simulate anonymous walks of length L for each node, and we want to represent the graph as a probability distribution of all these different walks. So the embedding would be an n-dimensional vector where n is the number of possible walks, and each dimension corresponds to the probability of a certain anonymous walk. So for example, if the length is 3, then the number of possible walks is 5. And possible walks would be staying on the first node 3 times, staying on the first node and moving to a new node, moving to a new node and returning to the first node, moving to a new node and staying on that node, or moving to 2 new nodes. So the embedding in this case would be a 5-dimensional vector where each dimension corresponds to the probability of having a walk of 1, 1, 1, 1, 1, 2, 1, 2, 1, 1, 2, 2, or 1, 2, 3. So finding all anonymous walks in a graph can be infeasible. As we saw, if we have length being 12, that's going to be over 4 million walks. So we sample to find a set of m walks to create a probability distribution. So the distribution should have an error of more than epsilon with probability less than delta. And using this equation here, that gives us a sample size. So we can just plug in epsilon or delta, depending on what we want. So, for example, if the length of our walk is 7, then we have 877 possible walks. So if epsilon is 0.1 and delta is 0.01, then we need to generate n equals 122,500 anonymous walks. We can also use this anonymous walk to create walk embeddings. So our goal is to learn an embedding for every walk in the graph, for every anonymous walk in the graph, and we want to concatenate these embeddings to create a graph embedding. So what we do is that we run t different random walks of length L starting from node U. And so that's where we would use sampling so that we don't have to go through every walk in the graph. And then we want to learn to predict walks that co-occur in a delta size window. So what that means is that given some existing walks, we want to know what is the probability of getting a different kind of walk. And we can estimate the embedding for a given anonymous walk using the following loss function. And if we apply softmax to that loss function, we can get the following parameterized log probability, where cat over 1 to delta is just the average of the of anonymous walk embeddings in the window concatenated with the graph embedding. Yeah. So if we want to use graph embeddings, it's pretty similar to how we would use node embeddings. We can use the inner product similarity of 2 different embeddings, or we can provide the graph embedding as an input to a neural network classification system. So to summarize, we talked about what graph representation learning is, and we discussed how node embeddings are able to represent the node similarity in a graph, and how random walks are able to estimate the similarity between vectors, depending on if we want homophily or structural equivalence. And we also discussed graph embeddings using a variety of techniques. And for further learning, you can use the Stanford CS 224 machine learning with graphs by Professor Drew Leskavec. He actually developed the node-to-vec strategy that we discussed earlier. And there's also this YouTube series by Philip Brunenberg, Graph Databases in Neo4j. And there's also a very useful textbook by William L. Hamilton, which is named Graph Representation Learning. And yeah, that's all I have. Thank you.
Hey, Adarsh, one question is, what about edge embeddings and edge representations? Any resources where I could learn about those? I guess you didn't talk about those, although you talked about graphs, and you can, yeah, I didn't fully understand like where to the edge embeddings come in, because you still have subgraphs that are connected by multiple edges. So would you not need some representation for edges as well?
Sorry, could you repeat that?
Would you not need some sort of representation for edges as well, and not just the nodes? So I guess I didn't quite catch how you could go to graph embedding from node embeddings without talking about edge embeddings.
Oh, okay, yeah. So what we do for node embedding, so edges are pretty much just representing that that they're just a connection between 2 different nodes. So it's much easier for us to basically, how do you say? It's
code.
Yeah, it's much easier for us to basically for the vector embedding for a node to have just absorbed that edge information.
I see, because the way you are training it, you're already encoding the edge information by the fact that you are walking either in an anonymous walk or a random walk through the edges. So that information is already encoded, isn't it?
Exactly. I think I actually just saw a question in chat about yeah. So how does graph embedding solve the transductive problem? So yeah, the graph embedding that we were talking about here, it's still using the shallow encoding system like the node embedding, so it doesn't quite address the transductor problem. Yeah, that's just one issue with the graph embedding. The goal of graph embeddings is to represent the graph as a whole. So it doesn't. It's still using the shallow encoding system, but it's better at representing graph at a higher level as compared to node embeddings. Any other questions? Thank you.
Perhaps one more question. There's any cases like adopting two embeddings, one for the structure similarity, the other for the what's the homomorphic, and using two set of embeddings simultaneously.
So sorry, can you repeat that?
Yeah. So you mentioned that usually the embedding is biased towards one. One towards embedding technique is biased towards one. Some towards structure similarities of the graph, and some bias towards homomorphic of the nodes. And I'm just curious about any cases that two set of embedding approach are used at the same time.
So okay. So I guess what you're saying is that we use two different embedding strategies at the same time. Is that right?
Yes.
Yeah. So those would be two different embedding spaces. Yeah. So you could focus on structural equivalence for one embedding space and then homophily for another. But those, and yeah, that would allow you to get a more full picture of the graph. But yeah, those would be two different embedding spaces. You wouldn't be able to combine that information. Yeah.
All right, thank you, Adarsh, for this very nice presentation. Adarsh, just to remind you folks, he's a first-year college student and he's doing his internship here at SupportVectors lab, and very well presented introduction to the topic. Thank you. With that, I'll stop the YouTube recording so people and then open it out to